Number 6, we will discuss about pipes in series, pipes in parallel, and empirical equations for pipe flow. So before that, we discuss some topics that we discussed in the last lecture. So in the last lecture, we studied about laminar flow and turbulent flow velocity profiles. So I will give a brief recap about that to refresh your memories. We discussed that for a circular pipe flowing full, the Reynolds number is given by RH is equal to R naught by 2. Clear? Where R naught, it is measured from the center of the pipe. This is R naught. It is measured from the center of the pipe towards the wall of the pipe. Now we already studied before that the head loss due to the friction, it is given by this expression. So this tau naught bar, we can replace with tau naught here. So we replace this with tau naught, and this RH that we can put here, and we get this value. So we already derived this before, and as I said that if we proceed in a similar fashion, and rather than considering R naught and tau naught, if we consider R and we consider tau, so this is how we will get this expression here. This is the expression that we will get. Clear? So now when we compare these two, when we compare this equation 1 with this equation 2, what we get? We will get this expression. And this is important expression because this gives us the shear stress at any distance r from the center of the pipe. If we know the shear stress at the pipe wall, then we can calculate the shear stress at any distance r. Now we already know that from here, this equation here, if we equate this with the Darcy-Weisbach formula, so then from here we get this relationship that tau naught is equal to F by 4 rho into V square by 2. Now this is to calculate the shear stress at the pipe wall. And once you calculate this shear stress you can put here to calculate the shear stress at any distance r. Now this equation, it can be used for laminar flow and it can be used for turbulent flow both. Clear? Then based on those equations, we already come up with this V is equal to this factor. So now for laminar flow, HF, this is given by this equation here. And this equation we studied that this is known as the Hagen-Poiseuille law for laminar flow in tubes. So Hagen was a German engineer and Poiseuille was a French scientist, a medical doctor, and they independently conducted experiment and developed these equations. So that's why this equation for head loss, HF, so this is known as the Hagen-Poiseuille law. This is known as the Hagen-Poiseuille law. And as I said that this equation you can use to calculate the head loss due to friction when the flow is laminar flow. When we have laminar flow, you can use this equation to calculate the head loss due to the friction. Clear? And also the striking feature of this equation is that in this case you can see that the head loss this is proportional to the first power of velocity, and this is what is experimentally verified, that in case of laminar flow, the head loss is proportional to the first power of the velocity of flow of fluid in pipes. Now when we compare this HF with the Darcy-Weisbach equation, when you compare this with the Darcy-Weisbach equation, so we get an equation for the friction factor. So we get that F is equal to 64 by R, where R is the Reynolds number. So you apply this equation to calculate HF, or you apply this equation to calculate F. You will get the same value for HF. F coming from here, and then you put this F in the Darcy-Weisbach equation and you calculate HF. So you will get the same value as this HF when the flow is laminar flow. Then we discuss about turbulent flow. So in case of laminar flow, we have the expression for the shear stress that is based on Newton's law of viscosity. So proceeding in a similar fashion, we said that for turbulent flow, the shear stress can be represented by this expression, where in this expression, this eta, this is the eddy viscosity. This eta is the eddy viscosity. And this is not a constant for a given fluid, but it depends on the turbulence of flow. So just like we have mu that is written for laminar shear stress, that in case of laminar shear stress, so what we have is that when the flow is laminar, so then in that case we studied that this tau, this is equal to mu into du by dy. This is in case of laminar flow. So in this case you already see that this mu, this is a fluid property, and this is constant for a fluid flow for a given temperature, and we can read this value from the tables available in books for different temperatures. But in this case, in case of turbulent shear stress, this eddy viscosity is not a constant for any given fluid, but it depends on the turbulence of the flow. That is why it becomes very difficult to measure this turbulent shear stress, because eddy viscosity, it will change from point to point in the same fluid for different turbulence. So in any case, the total shear stress in turbulent flow, that will be equal to the laminar shear stress plus the turbulent shear stress. And why it is so? Because in near the wall of the boundary of the pipe here, the viscous forces are dominating. So when the viscous forces are dominating, due to the viscous forces, that will be the shear stress that will be generated, that is known as the laminar shear stress. As I said before, it is not a true laminar flow near the wall, but it is a laminar like flow. This is what is written in your textbook. Clear? So that is why the total shear stress, that will be equal to the laminar shear stress plus the turbulent shear stress. And you can see that as we move away from the wall towards the center of the pipe, the turbulent shear stress, it increases, and the laminar shear stress decreases in value. And of course at the center of the pipe, then the shear stress is 0. So that is why we can write down the total shear stress as the sum of laminar shear stress plus the turbulent shear stress. And we can also write down equation in this form, where epsilon, it is known as the kinematic eddy viscosity. So this is the first expression that we can represent the shear stress in case of turbulent flow. Similarly, there is a second expression, and as I said, that the second expression, that is based on the momentum principle. So the momentum principle we apply in fluid mechanics and hydraulics in order to calculate the forces in fluid flow. Whenever you want to calculate the forces, we cannot apply the continuity equation, neither we can apply the Bernoulli equation to calculate forces, because continuity equation is law of conservation of mass and the Bernoulli equation is based on law of conservation of energy. So if we want to calculate the forces in fluid flow, then we have to apply the momentum equation. So the momentum equation says that this force, this is equal to the rate of change of momentum of the fluid body. Clear? This is equal to the rate of change of momentum of the fluid body. So in this case, how to calculate this? This rho is the density of the fluid. Now we need to calculate the discharge and the change in the velocity. So for that case, we consider this figure here. In this figure, you can see that in case of turbulent flow, we studied that in case of turbulent flow, the velocity has fluctuations. So let's say this represents the time. So with respect to time, and if I plot the velocity in the x direction, that is represented by u. So what we have is, one is the average velocity, that is represented by a straight line, and that we write down as u with a bar. So this is the time average. And then what we have, that we have these fluctuations. Then in this case, what we have is that we have fluctuations. This is due to the turbulence. So this will go up and down, and this will happen in all the three directions. Clear? So at any point here, if you consider this here, then this is can be represented by u dash. This can be represented by u dash. So at any instant, if you want to calculate the velocity, that will be equal to the instantaneous velocity will be equal to the time average plus, in this case, that will be equal to u dash. Clear? So now in this case, what we see in this diagram here, so if you look at this diagram, then in this case what will happen, that we already studied that in case of laminar flow, the momentum transfer between the different layers, that is due to the molecules. But in case of turbulent flow, that is due to the pockets of molecules that moves from one layer to another layer, and because of that the momentum transfer occurs. So now you can see that this is a packet, a fluid particle, a packet of fluids, and then in that case what we have is that, in that case what we have, that we have this fluctuating component. So this fluctuating component, this is v dash. This v dash, this is the fluctuating component. And in this case what we have is that because of this fluctuating component, there will be an upward motion of this fluid particle. Clear? There will be an upward motion of this fluid particle. Now in this case, because of this, there will be a flow of the fluid across this line here. So if we consider this line here, so in here we consider an area dA. So now what will be the flow? the flow in this case, that will be need to calculate. That discharge we need to calculate in this equation. Clear? So in that case, this discharge will be V dash times dA, because this is the velocity and it is occurring through this area dA. So this will be equal to V dash times dA. Now the velocity at this point here, for example, we have u at one point, and then when it moves to another point, then it is u plus u dash. This is what you can see, delta u equal to u dash. So that is why the final velocity, that will be u plus u dash. This is due to the fluctuation minus u. Clear? That it has in this lower layer. So now this is how it comes, this delta v. So this delta v, this comes here, u plus u dash minus u. So now when we simplify this equation, what we get is that this u and this u cancel out. Clear? And what we are left is with rho u dash v dash into dA. This is the force. Clear? So now if we consider this over a period of time that is sufficiently long to include large number of fluctuations, then in that case the shear stress, that will be equal to F by dA. The shear stress, that will be equal to F by dA. So when you divide this by dA, this is coming from here, you can see here this, so this comes here, we want to calculate the shear stress, and this will be equal to minus rho into u dash v dash bar, because we are averaging the condition, so that is why this bar appears. Clear? So now this shear stress, this is now equal to minus rho into u dash v dash bar. We are averaging this over a time sufficiently long to include for all the fluctuations. Clear? Because this u dash v dash, these are the fluctuations. And then in modern turbulence theory, this is known as the Reynolds stress. This component is known as the Reynolds stress. So now we studied that in this equation here, what you can see that as I try to explain here, that how this negative sign comes. How this negative sign comes. So now in this case, you can see here in this diagram that this laminar and turbulent flow. Clear? So what we have is, as I said already, that in case of laminar flow, the molecules, they interchange between the two layers. You can see in this diagram that in case of laminar flow, the molecules, they interchange between the different layers. But in case of turbulent flow, rather than the molecules, what we have, fluid packets, which we call as the eddies. So these fluid packets, they move, clear, randomly, and because of that the interchange of momentum takes place between the different layers in case of turbulent flow. So this is what I explained last time. Now as you can see, I tried to explain that from where this negative sign comes. Clear? Why in this shear stress we have the negative sign, minus rho into u dash v dash bar. So this negative sign here, you can see that whenever we have a fluid here, so it moves from this layer to this layer, upper layer. And as you can see the velocity profile, which is drawn here. So when this fluid particle, this is the fluid particle or pocket of fluid, which is eddy, when it moves from this layer to this layer. Clear? So this is in the positive y direction. So that is why we have plus v dash. But you can see that when this particle moves from a layer which has a less velocity as compared to this layer which has more velocity. So that is why this particle will bring a change in the velocity which will be minus u dash. Clear? Because it is moving from a low velocity layer to a higher velocity layer. So it will try to slow down. So that's why the change that it will bring in this layer, that will be negative. So that is why in this case, this plus v dash is related with the minus v dash. And conversely, if any particle moves in this direction, then in that case what will happen? Then for this case we will have minus v dash, because you move in opposite direction, minus negative y axis. But then in that case the fluid pocket, it will move to from higher velocity region to a lower velocity region. So that's why it will bring a change. That will be what? That will be plus. That will be plus u dash. So then in that case, you can see that still this product will be minus. Or in this case, still the correlation is negative. This is what we say, that the correlation is negative. So what we have is that we have this u dash, clear, and we have this v dash, and then we average over a long time. So this is negative, clear. So this is negative, so this is less than 0. So what will happen? That it will make the shear stress greater than 0. So if you study for example, the Indian books, you will not find that a negative sign is written. They directly proceed with that. But anyhow, according to our textbook, we need to put this negative sign to correctly represent them. Clear? So it means that the correlation is negative. And this is another diagram. You can see that this fluctuating component in the x direction, you can see that it can be minus u dash and it can be plus u dash. So if we move in this direction, then this plus u dash, it will be connected with this minus u dash. And if we move in this direction, then in that case we have minus v dash, and it will be correlated with this plus u dash. So this is, I just try to explain that in the Reynolds stress, why we write down this negative sign here. So this is an explanation to how we write down this Reynolds stress. Now if we proceed, so this is now the expression that we get, clear? And this is known as the Reynolds stress, because you get the stress units. Shear stress is given by this quantity, clear? But then the problem is that we have to measure these product of fluctuations for a long period of time. So that's why it is very difficult to measure this quantity. So what we have to do is that we have to express this shear stress in the form of equation that we can measure. So what we did is that in order to simplify this question, we bring in the concept of mixing length L. And this idea of mixing length L, it was given by Prandtl. So Prandtl, he gave the idea of this mixing length, and that is what is known as, in some texts it is written, Prandtl mixing length theory. And in that mixing length theory, he stated that what is this mixing length L? It is that distance, you can see here, it is that distance that a fluid from one layer will move from another layer so that the momentum transfer takes place. As we already discussed, there is a momentum transfer between the two layers. Either the fluid particle moves from lower layer to upper layer or from upper layer to lower layer. So it says that it is that distance in which this momentum transfer between the two layers will occur. Clear? Or another definition is that when a particle moves from this lower layer to a higher layer, it will move in such a distance L before it loses its initial velocity, because it moves to a higher velocity layer. Clear? So this is how we define the mixing length L. Clear? So now, based on this concept, how to calculate the mixing length L, if we compare these similar triangle, this is du, and this is the change in the velocity, and this is in a distance dy. Clear? Here. Similarly, we have this delta u that we take as equal to u dash bar. So this delta u, that will be equal to the time average of these fluctuation in the x direction. So now we have this u dash bar divided by this distance, which is L, also equal to du divided by dy. So now from here, similar triangles, we get L is equal to u dash bar divided by du by dy, and it is written in absolute because it has plus minus sign that we already discussed. So now delta u is equal to L into du by dy, and from this equation here again we have u dash bar that is equal to L into du by dy. So this is the value of u dash bar. Prandtl also reasoned that this fluctuation in the y direction, that will be equal to some constant of fluctuation in the x direction. Clear? So based on this, we can write down this expression as v dash bar equal to c into L du by dy. And also this quantity here, this can be written as L into du by dy and L into dy by di. And this c we bring into this mixing length L. So that is why this component now equal to L square into du by dy whole square. So now the shear stress, which was represented by this Reynolds number, is now represented in this term. And now this equation or this form of the shear stress we can measure. This we can measure because this L now we can measure, and this can be represented as a function of the pipe radius. So the shear stress you can easily calculate. You have the head loss, and then from that we can easily calculate the shear stress, the pipe wall shear stress. Clear? And the shear stress, and then du by dy we can measure. Rho is the fluid property, so it means that we can express this L as a function of the pipe radius, and now in this equation all the quantities we can measure. So the total shear stress is now given by this expression here. So this is the laminar shear stress, and this is the turbulent shear stress. So the total shear stress can now be written in this equation form. Now, how to determine the value of this mixing length L? So this Prandtl assumed that the mixing length L is proportional to the distance from the pipe wall, and it can be written as L near the pipe wall. As we move towards the center of the pipe, L is proportional to y, where y is the distance from the pipe wall. So now this k becomes a constant. A is proportional to y. So when you change proportionality sign into equality, we multiply by a constant, and this constant experiments have confirmed that this k is equal to 0.4. So now using this equation we can calculate L, and that L we can put here to easily calculate the shear stress. Clear? Then we discuss about the velocity profile in turbulent flow. So in that case we studied that in case of turbulent flow, the velocity profile, it can be represented because you can see here the log. So that's why it can be represented by a logarithmic velocity profile. And we already saw video last time in the class that experiments also support that it follows a logarithmic velocity profile. Clear? So this equation, this has a proof, but for the sake of time saving, I skip the derivation. We only use this equation in the problems also to calculate the velocity at any distance r from the center line of the pipe. Clear? We can use this equation to calculate velocity at any distance r from the center line of the pipe. So in case of turbulent flow, it follows a logarithmic velocity profile. And in case of parabola, laminar, the parabolic velocity profile is followed. Now the next topic is pipes in series and pipes in parallel. So most of the piping systems encountered in practice, such as water distribution systems in cities or commercial or residential establishments, involve numerous parallel and series connections. Clear? So either we are supplying of fluid into the system or we are discharging fluid from the system. So now our next topic is to study the analysis of pipes in series and pipes in parallel. So why we need to study this topic? As you can see that we have water distribution systems around us. They either supply the water into the system or take the water, means discharge the water from the system. In our cities, commercial areas, such as we have, for example, industries or in residential establishments. Clear? So that involve numerous parallel and series connections. Pipes are connected in parallel or in series that supply fluid into the system or discharge fluid from a system. You can see in this diagram a piping network in an industry facility. So you can see here the complex piping network system in which we can see that the pipes are connected in series and in parallel. So when we have to do the analysis of these pipes, then we have to apply the concepts that we are going to study in this topic. Because before this, all the pipe flow problems that we studied so far, that include single pipe flow problems. That only one pipe, the flow occurs, for example, connecting two reservoirs. We studied only such type of problems so far. Now, in this topic, we will study that different pipes will be connected in series or in parallel, and then we how proceed to do the analysis of such pipe systems. So first we take pipes in series. So as you can see here in this diagram, we want to convey the fluid from reservoir A to reservoir B. And now the water or any fluid that is conveyed through these three pipes in this case. There can be several pipes, but just for understanding purposes as an example, here you can see that three pipes are connected. They are of different diameter and the liquid is transported to this reservoir B. So now if the pipe is made up of sections of different diameters, in this case, you can see here the three pipes, they are of different diameters. The continuity and the energy equations establish the following two simple relations which must be satisfied. So when different pipes of different diameters, when they are connected in series, then they must satisfy these two relations. The first one is the continuity equation. It means that Q is equal to Q1 equal to Q2 equal to Q3 and so on. When we have large number of pipes but they are connected in series, the continuity equation says that the same discharge will flow through all the pipes, because you can see here the liquid, it enters here at this point and the liquid exit at this point here. There is no other entrance and exit points. So that is why the continuity equation says that the same discharge will flow through all the pipes. Clear? And the second one is the energy equation. The energy equation says that the total head loss, that will be equal to the sum of head losses through all the pipes. So for example, if we have 3 pipes, so then in that case this is equal to head loss that occurs through pipe 1. Similarly, we have head loss that occurs through pipe 2 and head loss that occurs through pipe 3. When we add them, we will get the total head loss, HL. And if we have large number of pipes, they are connected in series, then it will continue. So it means that to satisfy the energy equation, the head loss, the total head loss will be equal to sum of the head losses through all the pipes connected in series. And how this happens, that why we have this situation, because in this case you can see that the total head loss, that will be simply equal to delta Z, the difference of water level between the two reservoirs A and B. We already solved a problem, but you can see here, if I consider any fluid particle here, let's say I consider here any particle 1, and then I consider another particle here at the surface of reservoir B. Let's say this is particle 2. When you apply the energy equation, Bernoulli equation, but we include the head losses, the energy equation, so we have P1 by gamma. Similarly, V1 square by 2G plus Z1 at this point 1 here, and this will be equal to P2 by gamma V2 square by 2G plus Z2 at this point here. So plus HL. This HL is the head loss for the entire system. We now consider the entire system. Clear? So then in that case, you can see that this will be equal to 0. This is 0, because here the atmospheric pressure V1 square by 2G, this is 0, because the velocity here is very small at this point 1. And P2 by gamma is 0, because this pressure is again atmospheric here. And similarly, this V2 square by 2G, that is equal to 0, because here again the velocity is very, very small. So now what we are left? We are left with this Z1 and Z2, and also we have this HL. So Z1 minus Z2. What we are left from this equation? We have this Z1, and this is equal to Z2 plus HL. Or we can write down that this Z1 minus Z2, this is equal to HL. And this Z1 minus Z2, this is equal to delta Z. So this is how this HL is equal to delta Z. So now remember, whenever the pipes, when they are connected in series, these two conditions must be satisfied. One is the continuity equation. It means that the same discharge will occur through all the pipes when they are connected in series. And the energy equation says that the total head loss through the whole system, through the entire system, that will be equal to sum of the head losses, the individual head losses through all the pipes connected in series. So what we can say is that, to summarize the discussion, when pipes are connected in series, the flow rate is the same in each pipe, and the total head loss is the sum of the head losses in individual pipes. Clear? So now, to do the analysis of pipes when they are connected in series, we can have two cases. The first case is that discharge will be given to us, this will be given, and it will be required to calculate the head loss. And the second case is that head loss is given and it will be required to calculate the discharge. So now when we have pipes connected in series, so we can face two types of problems. In the first case, discharge will be given, so it will be asked in the problem to calculate the head loss. And the second case, head loss will be given and it will be asked to calculate the discharge. So now, how to solve such type of problems? For example, we consider case 1 in which now discharge is given and we are going to calculate the head loss. So how to proceed? The head loss, that will be equal to the sum of the head losses in the individual pipes, as we already discussed, and we already know that this HL, this is given by the Darcy-Weisbach formula. So for pipe 1, this will be equal to F1 L1 by D1 V1 square by 2G. And then for pipe 2, it will be given by this expression. For pipe 3, it will be given by this expression, and so on. If 3 pipes are given, it will be the sum of these 3 components. If 10 pipes are given, then it will be the sum of 10 components for all the pipes connected in series. So now in this case, these are given, clear, from Darcy-Weisbach formula. So HL we can calculate, clear. So let's say the discharge is given. So when the discharge is given, you can calculate V1, clear. So V1 will be equal to this Q divided by area A1. Similarly, you can calculate V2. V2 will be equal to Q divided by area A2. Similarly, you can calculate V3 and so on. That will be equal to Q divided by area A3. So this will be actually Q3, this will be Q2, and this will be Q1. But we already know that your total discharge, that will be equal to Q will be equal to Q1, and this will be equal to Q2, as we stated from continuity that the same discharge will occur through all the pipes. So you can calculate V1, you can calculate V2, you can calculate V3, and that you can put here. This V1 you can put here, in here, and then this V2 that you can put here, and similarly this V3 you can put here. So G is known, L will be given to you, the diameter will be known to us for the pipes. Now the question is from where F will come. So this F1, F2 and F3 and so on, either this will be given to you in a problem. So if they are given, everything is known, you can easily calculate the head loss. That you can easily calculate, and this is what we need to calculate, because head loss we need to calculate. But if F1, F2 and F3, they are not given, then essentially it becomes a trial and error procedure. Just like we solved a single pipe flow problems, in that case, you can assume some values for this F1, F2 and F3 and so on. And then in the end, you have to verify. You will calculate the Reynolds number and the relative roughness, and then you use the Haaland equation, Colebrook equation or Moody's diagram, and then again you will calculate these f values, and this will continue. The trials will continue unless and until the assumed value or f that becomes equal to the calculated value of f. Then the solution will terminate, and those f values you can put here, clear, and you can easily calculate then this HL. So this is the procedure how we solve case 1 problem when discharge is given and head loss is unknown. So in that case, what you do, that you will use the Darcy-Weisbach equation here, and then because the same discharge occurs through all the pipes, you can easily calculate the corresponding velocities that you can put here, and if f values are known, you can just use this equation, put all the values, and you can calculate the total head loss. The second case is that now in this case, this HL is given, the head loss is given to you, and you are required to calculate the discharge. So how to proceed with this? We have two methods for this. The first one is known as the equivalent velocity head method. The first method is known as the equivalent velocity head method, and the second method is known as the equivalent length method. So when head loss is given to us and we are required to calculate the discharge, then in that case you can apply any of these two methods. Either you apply the equivalent velocity head method, or you can apply the equivalent length method to solve the problem, and both the problems will give you the same answer. When you apply any of this method, you will get the same answer. Now in the previous editions of the textbook, they explain both of these methods, but now if you study the 10th edition of the book, only they explain the equivalent velocity head method. But anyhow, in this course I will also explain the equivalent length method, how we proceed in order to solve the case 2 problems. Clear? In your book, textbook, now the 10th edition, only they explain this first method. But anyhow, we will proceed and we will apply both the methods in order to solve case 2 problems. Now first we consider the equivalent velocity head method. So in this method, velocity in each section is converted into equivalent velocities by using the continuity equation. So in this method, what we do is that, for example, we already know that the discharge Q1 is equal to Q2 is equal to Q3. And remember what we are doing essentially here, that now Q is given. This Q is given and we are going to calculate the head loss. So proceeding that, now Q is given, clear? So because Q is given, the discharge is given, and from continuity, this Q is equal to Q1 equal to Q2 equal to Q3 for 3 pipes connected in series. And if we have large number of pipes connected in series, then it will continue up to that, clear? So now this is known, this discharge is known. Now from continuity, what we can write down, that this A1 V1 is equal to A2 V2 is equal to A3 V3. Now from here, we will express all the velocities in terms of, let's say, V1, clear? So this will be the equivalent velocity. This is how the concept comes, equivalent velocity, that essentially we are expressing other velocities in terms of V1 using the continuity equation. You can see here, this V2 is now expressed in terms of V1 using the continuity equation. When you compare these two here in this equation, you can see here, when I compare these two here, so this is what we get, V1 in terms of V2 in terms of V1, clear? Because we say that express all the velocities in terms of V1. Similarly, what you can see here, that now if we compare What we compare? Now you compare these two here. A1 V1 is equal to A3 V3. So now essentially what we are doing, that we are expressing V3 in terms of V1 now. And you will proceed like this. If we have, for example, A4 V4, then V4 in terms of V1 and so on. So we are expressing all the velocities other than V1 in terms of V1. If you simplify this, this is what we get. V2 is now equal to this, and V3 is now equal to this equation here. So now what we will do, that this HL, this will be equal to sum of all this. What we did here is that the head loss, what we want to calculate, we want to calculate the head loss. This is unknown quantity in the problem. This is unknown. So we already stated that this HL, this will be equal to what? If I go back here, so we already studied that this HL, this is equal to here, this equation. HL is equal to HL1 plus HL2 plus HL3 and so on. So this comes here, and this is what you have written. Clear? HL1, HL2, HL3 and so on. Clear? For example, this is HL3. So now V1 square by 2G, because we expresses V2 that we written here and V3 that we written here, we express them in terms of V1 and V1. You can see here. That's why this V1 square by 2G can be written outside the bracket. And now in this case, it is easy to calculate this HL. Clear? V1 you can calculate because Q is given. This is given. This is known to us. We need to only calculate this HL. So from here, this, what is the problem here in this case? That we are going to calculate this discharge here. Sorry, we are going to calculate the discharge. HL is given to us. So now when we proceed in here, this is the discharge we have to calculate. Clear? This we have to calculate. And this HL is given to us. This is given to us. This HL is given to us. So now the only unknown in this formula is what? This is V1. Clear? V1 is unknown. So now we can easily calculate the discharge. That will be equal to, Q will be equal to A1 and V1 here. So in this equation, here now we are able to calculate Q, and the same discharge using this formula you can calculate V2. Since V1 is known, that you can put here. You can calculate V2, and then you can calculate Q2. So Q2, that will be equal to area A2 into V2. That you can calculate. Similarly, this V1 you put here, and you can calculate V3. So this Q3, that will be equal to A3 into V3. So you should get the same result, because we already know that in here Q1 is equal to Q2 is equal to Q3. So this is how we calculate the discharge when the head loss is given. So in this what we essentially did is that we express all the velocities in terms of one velocity, which is, let's say, v1 here. You can also express these velocities in terms of v2, all the velocities in terms of v2 or in terms of v3. Still you will get the same result. Clear? So this is how we will solve the problem when the head loss is given to us and the discharge that we have to calculate. So you can only just calculate this and these two. This will serve as a check. Now next we consider the equivalent length method. The second method, the first method was equivalent velocity, this one here, this one equivalent velocity head method. The second one is the equivalent length method. So in this method, all the pipes, they are expressed in terms of equivalent length of a given pipe. So just like in the previous case, we were expressing all the velocities in terms of an equivalent velocity for any given pipe, which may be pipe 1, which may be pipe 2 or pipe 3 and so on. In this case, what we do is that the pipes, they are expressed in terms of equivalent length now. By equivalent length, what we mean? The length LE of a pipe of certain diameter DE and friction factor Fe, for which the same flow will give the same head loss, is the pipe under consideration of length L, diameter D and friction factor F. For example, to understand this, we consider two pipes. One is pipe 1, clear, and the second one is, let's say, the effective pipe E. So for the same head loss, clear, that will give us the same flow, that will give us the same head loss. So what we say is that HL, the head loss for pipe 1, this is for pipe 1, and for any effective pipe that we will consider, this is the head loss through that pipe. So this we represent by this Darcy-Weisbach equation. And from here, we will get this equation 1. Now in this equation 1, I write down in terms of this effective length LE1. Clear? So 2G cancel out. That's why this is gone. This 2G cancel out here with this 2G, and the other we compare. So what this equation tells us? This equation tells us that what should be the length of that effective pipe here. That will give the same head loss as the pipe 1. You can see here we are equating HL1 is equal to HLE. So it means that what should be the length of this pipe that will give us the same head loss is the head loss in pipe 1. Clear? What should be the length of that pipe? So Q1 is equal to QE. From here, Q1 is equal to QE because we have pipes in series. So the same discharge will occur through all the pipes. From here, the continuity equation A1 V1 is equal to AE into VE. And then from here, you just put pi by 4 into DE square divided by pi by 4, the cross-sectional area. So you can see here this pi by 4, this will cancel out. And we can write down this in the form of equation 2. So now this equation 2 we can bring and put here. You can see here V1 square divided by VE square. So if we put these values you will get this expression for LE1. So now instead of the velocities here, instead of this velocity here, this one, we just put this here. Now we get this expression. Similarly, if you proceed, so we will get LE2 and LE3 and so on. So then the total effective length that will be for the effective pipe, that will be equal to LE1, LE2 plus and plus LE3. Once we are able to calculate this LE, then for that effective pipe, this HL, the head loss, that will be equal to given by this expression. Clear? And from here we can calculate VE, because head loss is given. The head loss in this case is given to us. This is what we have case 2, that head loss is given and we want to calculate the discharge. So now this is given and you can calculate discharge. From here VE we can calculate, and then Q is equal to AE into VE, and this is how we come up with this discharge. And this discharge will be same for all the pipes. This Q will be equal to this Q here, this will be equal to Q1 equal to Q2 equal to Q3 if we have 3 pipes. If we have more than 3 pipes, then it will continue. So essentially in this method what we are doing is that we are expressing, what we are doing, we are expressing the length of all the pipes in terms of an effective pipe E. And this effective pipe E, we will solve a problem. It can be one of the 3 pipes. Clear? For example, we have 3 pipes given in a problem, and then if we are going to select which one will be the effective pipe, because now the question is that if we have 3 pipes, pipe 1, pipe 2, pipe 3, then which one will be selected as the effective pipe? So it says that, let's say we have pipe 1, clear? We have pipe 1, similarly we have pipe 2 and we have pipe 3. And now we have to consider the effective pipe, that which one can be the effective pipe. So you can select anyone to be the effective pipe. Clear? Either you can select pipe 1 to be effective, then in that case your LE1, it must be then same as L1. Clear? And then you have to calculate this LE1, E2 in terms of L1, and similarly LE3 in terms of L1. You can select pipe 2 to be effective pipe. Then we have to express 1 and 3 in terms of that. Or you can select pipe 3 to be the effective pipe. Then you have to express 1 and 2 in terms of 3. So it means that when we solve and when we apply the equivalent length method, then in that case any of the given, for example we have 3 pipes or even 4 pipes or 5 pipes, clear, and so on, you continue, anyone can be selected as the effective pipe. And then we express other pipes in terms of the effective pipe for this selected pipe, and then this is how we proceed to solve the pipe flow problems and calculate the discharge. This is what we are going to do in the end. We are going to calculate the discharge. Clear?